Okay, so the last thing we had shown that the electric field at the top of a surface minus the electric field at the bottom of the surface take their component perpendicular to the surface. This was equal to 4 pi sigma, 4 pi over epsilon 0 times sigma, where if this is our surface and you take this one as your n vector, this is the top side, this is the bottom side. So this basically you can use to evaluate what the surface charge density is if you know the electric field. And just calculate how much it changes across a given surface. If that change is finite, then it is proportional to the surface charge density. Well, so there is no 4 pi sigma over epsilon 0. Now let's try to apply it to a problem that we know. Two parallel plates separated by a distance d. Let's say d is very small. This is the area. D is very small. Now what I will assume that in between the area the electric field is uniform. Well, it's a very small area, very small difference, so I will just assume that it is uniform. So here, in fact, let's just for simplicity, let's assume that the electric field is uniform everywhere. We don't yet, I'm not claiming that the electric field is 0 outside. I don't know. I mean, we will see what the Gauss law tells me. Let's say that above the electric field is E1. In the middle, the electric field is E. And below the electric field, let's just call it E2. Now, if you remember in our first year classes, we said that E1 is equal to 0, E2 is equal to 0, and the E is perpendicular to the plates. But I'm not making that assumption yet. Now, we had derived this discontinuity relation using the Gauss law across any surface. Well, I can apply it over here first, at this point. Let's take n to be in this direction. If n is in that direction, E top is E1, E bottom is E dot n. This should be equal to, well, let's say this top surface, top plate has a charge density sigma, lower plate has charge density minus sigma. So this is equal to sigma over epsilon 0. Let's apply it at this point across my surface. N is still the same vector. And remember, n vector defined on a surface points from bottom to top. So at this point, when we say the top of the surface, well, that's the E. The bottom of the surface at that point is E2. That with n, this is equal to minus sigma over epsilon 0. So this is what the Gauss law tells me. The Gauss law doesn't tell me anything else. But these equations only tell me that E1 is equal to E2. I don't know what they are. Since I don't know what E1 and E2 are, I don't know what E is. So that, yes? Nothing yet. The only assumption I make is E1 is uniform, E is uniform, E2 is uniform. That is the only assumption I made. Right? If I don't make that assumption, I cannot really compare the first equation with the second equation, because E in the first equation and E in the second equation can be different. But once I assume that the E1, E2, and E, they are uniform, E in the first equation and E in the second equation, they are the same. And so E1 should be equal to E2. I cannot say that E1 is 0 or E2 is 0 without additional input. I cannot say that the E is in the vertical direction, that is E is proportional to N. All those things are additional inputs. Without those additional inputs, Gauss' law doesn't tell me what the electric field is. That is why it is important that you first study the symmetries of the problem, try to acquire some information about the electric field before trying to apply the Gauss' law. With those additional information, then you can say that the Gauss' law allows you to evaluate the electric field. Now, what are these E1 and E2? E1 and E2 will be basically the electric field created by some other charge distribution somewhere else, if they are in it. Well, if the only charges we have are these two plates, one thing is E1 should be equal to E2. That is one knowledge we have. Well, the problem is kind of the electric field created by sigma only, it's the plus sigma plate, and the electric field created by the minus sigma plate, they should be the same. They should have the same pattern, shifted by that difference d. The only difference is that the electric field should be pointing in opposite directions. So they should be creating the same electric field at this point, but pointing in opposite directions. One is pointing out, the electric field created by the positive plate should be pointing away from the positive plate. The other one should be pointing towards the negative plate. So they cancel. Only with this additional input we can say that E1 is equal to 0. And hence E2 is equal to 0. This is an additional information. It doesn't come from the Gauss law itself. Now, if E1 is equal to E2, they are both 0. We know that E dot N should be equal to sigma over epsilon 0. Still, that is not enough. Well, since the problem is translationally symmetric, if we translate it along the plates, nothing changes. If we rotate it, each plane in its plane around an axis perpendicular to these planes, nothing changes. So the only possibility is that the electric field should have this form, some number, multiply in either the n direction or the opposite the n direction. Now, sorry, here I have a minus sign. Now, this is my additional input. It doesn't come from the Gauss law. With this additional input, I can say that minus E is equal to sigma over epsilon 0. So E is equal to minus sigma over epsilon 0. So the electric field is minus sigma over epsilon 0 in the vertical direction. This is my additional input. Again, just using Gauss' law, you cannot calculate the electric field without additional input. So if you are applying the Gauss' law to find the electric field of a given charge distribution, you have to first find what is your additional input. What do you know about the electric field? If you go back to our previous example, well, if you look at your notes at our previous example, of this infinite wire with linear charge density lambda, we first said that, okay, the electric field, we don't know what it is, but it should have this form. This is our additional input. This plus the Gauss law allowed us to find that this E of R is nothing but 1 over 2 pi epsilon 0 lambda over R. Not just the Gauss law, this additional input plus the Gauss law allowed us to do that. Now, any questions on Gauss's law?
Hocam biz hani yukarıda D1 eşittir 2 0 dedik ya. Orayı nasıl belirledik? Hani başka yerde charge yoksa falan şeyler yok.
Well, let's see. Let me just look at this one, plus sigma plate. Let me study this problem. What do I know about the electric field here? Now, the electric field at this point and the electric field at that point, can they have different magnitudes? No, because basically, I mean, my charge distribution doesn't change if I just translate it horizontally. Nothing changes. So every point that is connected to another point horizontally by a horizontal translation should have the same electric field. Now, and this point and this point, if they are at the same distance from the plate, what can you say about the electric fields at those 2 points? Can they have different magnitudes? They cannot have different magnitudes because if I put a mirror on my plane, my charge distribution doesn't change. So if 2 points are connected by this mirror, they should have the same electric field. Of course, the mirror changes their direction. So if here the electric field is pointing upward, here it should be pointing downward. But they should have the same magnitude. So this already tells me that the electric field, it can depend on D. And it will be, let's say this is my z-axis. It can depend on my z-coordinate. I don't know, I might be looking at different points and with different z-axes. It cannot depend on x and y coordinate because they're all connected by horizontal translations. But it can depend in principle on the z-coordinate. It will be in the plus z-axis, plus z direction if z is larger than 0, and minus z if z is less than 0. And then we can take such a Gauss surface. This distance is the same distance as d. I can evaluate the Gauss integral over this surface. Let's say the area is A. And this integral will be just 2a times E of d. I'm not going into the detail. If you want, we can do that. But basically, it's the same. You just divide your integral into 3 parts, the top, the bottom, and the sides. The electric field is in the z direction, so there's no contribution from the sides. There's only contribution from the top and the bottom. On the top and on the bottom, the electric field, E and ds, they are in the same direction. And E is constant at the top and at the bottom, so I can just take it out in each one of those integrals. And both the top and the bottom just contribute E times A. I have 2 of them, twice E times A. And the Gauss law tells me that this should be equal to A times sigma over epsilon 0. A's cancel, so the electric field is sigma over twice epsilon 0. Now the crucial thing is this is independent of D. No matter how far away you are from the plate, the electric field is the same. Now, with this knowledge, the electric field is independent of the plate. Now, in fact, we could have said it without even using the Gauss law. Well, I will be deriving the electric fields. We said that they are on the z direction, the electric fields, by using the same arguments. We just said it's in the z direction. So these are my electric field lines. So basically their density is the same everywhere. It just means that the magnitude of the electric field is the same everywhere. I don't even use the Gauss law in this explanation, let's say. Well, if the electric field is the same everywhere, let's go back here. At this point, the positive plate will create an electric field away from the positive plate. The negative field will create an electric field towards the negative plate. That is, both of them will create electric fields in opposite directions at this point over here. And we know that their magnitudes have to be the same, just in opposite directions. Well, if you just add them up, you have two vectors having the same magnitude but pointing in opposite directions. Their sum is 0.
Hocam bunu elektrik alanını hesapladığım noktanın D'den çok büyük olduğu varsayımına göre mi söylüyorum?
No. I mean, D can be very small. D can be, let's say, over here. Now, the point can be over here, very close to the plate. Or it can be very far away from the plate. The electric field will be always 0. Of course, assuming we are making one assumption that the plate is very large. Ideally, it should be infinite. Because if the plate is not infinite, if you translate it horizontally, you are changing your charge distribution. It will look different. Only if the plates are infinitely wide, then horizontal translations do not make any change. Any questions? Now, the Gauss law we had derived from the divergence of the electric field. Now, let's look at the curl of the electric field. Now, again, there are different ways of studying the curl of an electric field. Remember, the curl will be relevant. For example, you take an area, not necessarily a closed area, better not a closed area, over some area. This is equal to the integral of the electric field around the boundary of that area. Well, the boundary will just form a closed loop. The left-hand side is not a closed area, but the right-hand side is a closed loop. So to study the curl, one thing we can do is just study the loop integral of the electric field. Or, in fact, let's just study E dot dl from point P1, P0 to P1. We obtain a closed loop if P0 and P1, they are the same point. Now, for simplicity, let's just take a single point that creates the electric field. So we have this plus Q charge. This is our point P0. This is our point P1. And let's just imagine such an arbitrary path. We already know what the electric field is of this single charge. Q over 4. The electric field at the point R, 4 pi epsilon 0. Let's just assume that the point charge is at origin, again for simplicity. It's R hat divided by R squared. Now we are going to evaluate E dot dl. And dl in spherical coordinates we can write as dr in the radial direction plus r d theta in the theta hat direction plus r sine theta. d phi in the phi hat direction. This is our dl. E dot dl is then just q over 4 pi epsilon 0 dr over r squared. So the integral of E dot dl from point P0 up to point P1, this is equal to q over 4 pi epsilon 0 dr over r squared from r0 up to r1. And you just evaluate the integral. It is q over 4 pi epsilon 0 minus 1 over r1 plus 1 over r0. One thing, the integral, it turned out that it is independent of your path, independent of how you go from point P0 to P1. Just take an arbitrary two paths and they will give you the same answer. Secondly, if P0 is equal to P1, then we know that R0 is equal to R1, which basically means that E dot dl, if P0 is equal to P1, it's a closed path. This is equal to 0. Well, we know that this is equal to the curl of the electric field integrated over our area is equal to 0. This should be true for all areas because we didn't assume anything about P0, P1, or the path that connects the two. So we just took an arbitrary closed path, and the integral of E dot dl over that arbitrary closed path is 0. But an arbitrary closed path is nothing but the boundary of an arbitrary area. Just consider an arbitrary area, then the curl of E integrated over that area is just 0. But that means curl of E is equal to 0. So we had already studied the divergence. Now we know that its curl is also 0. Well, let's do it in a more straightforward manner. This is one way of seeing that the curl of the electric field is 0. But we also can derive it in a different way. We know that the electric field at the point R is d cubed r prime, rho at r prime, r minus r prime divided by r minus r prime cube, 1 over 4 pi epsilon 0. We might not know what the rho is, but whatever rho is, the electric field and rho should be related in this form. Now, taking the curl of this, well, by the way, in this derivation, we had missed one step. This proves that the curl of the electric field of a point charge is 0. But if we don't have a point charge, we have many charges, then the electric field is nothing but the sum of them. Curl of the electric field is nothing but the curl of the electric fields created by each one of these point charges. Well, each one is 0, curl. So the sum is 0. So although we derive this for a point charge, it is 0 also for an arbitrary charge distribution. Now let's do it more generally using this general representation. Let's calculate the curl with respect to R of this function. Because that is the only thing that depends on R in my integral. If the curl of this thing is 0, then I can just put the curl inside my integral. Inside my integral, it will only act on this factor. And if the curl of this factor is 0, then the integral has 0 curl. Well, I will not be doing all of it. Let us just check the x component. Well, the x component will be derivative with respect to y of the z component of that vector field, which is z minus z prime divided by r minus r prime magnitude cube, minus derivative with respect to z of y minus y prime divided by, again, r minus r prime cube. Or let me write it in this form. Derivative with respect to y of z minus z prime divided by r minus r prime squared raised to the power 3/2 minus derivative with respect to z of y minus y prime divided by r minus r prime squared raised to the power 3/2. This is equal to, I will use the chain rule. Okay, z minus z prime, it doesn't depend on y, minus 3/2 1 over r minus r prime squared to the power 5/2 times the derivative with respect to y of, well, r minus r prime squared is x minus x prime squared plus y minus y prime squared plus z minus z prime squared minus, well, the derivative with respect to z is similarly minus 3/2 1 over r minus r prime squared raised to the power 5/2, derivative with respect to z of the same bracket equals almost the last step, z minus z prime times minus 3/2 1 over r minus r prime to the power 5 multiplied by, if I take the derivative with respect to y, I get twice y minus y prime minus y minus y prime minus 3/2 1 over r minus r prime to the 5th power. If you take the z derivative, it is just twice z minus z prime. But you see, these two factors are the same, these two terms. So this is equal to 0. But at least the x component of this curl is 0. You can repeat the same derivation for the y and the z components, and you will see that all of them are 0. So if we start from this one, if you take the curl of that electric field, this will be equal to 1 over 4 pi epsilon 0 d cubed r prime rho of r prime curl of, with respect to r, of r minus r prime divided by r minus r prime cube. This is 0. So the integral itself is 0. Now what I did over here, since the integral is with respect to r prime, but my derivatives are with respect to r, I can just exchange their order. I can put the differentiation inside my integration. And the only factor that depends on r is that r minus r prime over the magnitude cube, whose curl is just 0. So the curl of the electric field is always 0 in electrostatics. We also had calculated that this was rho over epsilon 0. So there is this vector field. We know its curl. We know its divergence. if you imagine a volume, an arbitrary volume, you know the charge density inside this volume, let's say it's rho, then if you know the value of the electric field on the boundary of this volume, then you can uniquely find the electric field everywhere inside this volume. You don't need to know the charge density out of this volume. If you know the value on the boundary, if you know the charge distribution inside, that's enough to determine the electric field everywhere inside your volume. You see, in this general expression for the electric field, if you want to determine the electric field in a given volume only, you need to know the charge density everywhere, not just inside that volume, but everywhere. Instead of knowing all the charges out of our volume, in this approach, we only need to know the value of the electric field on the boundary, or at least some properties of the electric field on the boundary would be enough for us. Yeah, next week we will see that we don't even need to know the value of the electric field, but we will define the electrostatic potential, and we need to know the value of the electrostatic potential on the boundary. If we know that, then we can determine the potential, and from the potential we can determine the electric field. Let's do an application of this one. Now we already said that if you have the curl of if you take the curl of a vector field integrated over an area, in the case of the electric field, this will be 0. And this means that the integral of the electric field around any closed path will be 0. It should be 0. Let's see what are the consequences. Just like the Gauss law, I mean, if you remember, knowing the Gauss law, we imagine an arbitrary surface, and applying the Gauss law to that arbitrary surface, we found out that the component of the electric field perpendicular to the surface need not be continuous. It can have a discontinuity, but it didn't tell us anything about the parallel component. Now, this law will tell us, the curl of the electric field will tell us how the parallel component changes. I will just again imagine my arbitrary surface. And this time imagine a very small loop. One side of the loop will be on one side of my surface. The other side of the loop will be on the other side of my surface. Well, I kind of exaggerated the loop, but imagine that it will be very thin and very small. Let's take, these are D. This length, let's call it A. Let's imagine the loop to go in the counterclockwise sense. And let's also give each segment, each side some name. This is side 1, this is side 2, this is side 3, this is side 4. E dot dl around this loop will be E dot dl over side 1 plus E dot dl over side 2 plus E dot dl over side 3 plus E dot dl over side 4. Now, eventually I will take the limit that this loop is very, very small. It will go to 0. I will take the limit that D goes to 0 first. Well, if D goes to 0, side 2 and side 4, well, they go to 0 because the length goes to 0. If the length goes to 0, the side goes to 0. The integral goes to 0. This is D goes to 0. So I'm left with only the integral over side 1 and the integral over side 3. Now let me call this vector n hat vector. This is not the normal. This is parallel to the surface. because side 1 and side 3, they are both parallel lines. They are parallel to the surface, and n is also parallel to the surface. So in side 1, dl on side 1 is nothing but the magnitude in the n direction, and dl on side 3 is dl, but this time in the minus n direction, because side 3 is going in the opposite direction. Now, A is very small. Since A is very small, along that line, the electric field does not change. It's almost a constant along segment part 3. The electric field is also almost constant on segment 1. If they are constant, I can just take them out of the integral. But if I take them out of the integral, what remains is E dot dl on part 1 plus E dot dl on side 3. So this is equal to E1 minus E3, electric field evaluated on the third side, times dl n in the n direction. This should be 0. Now I can cancel dl. Remember, A is small but not yet 0. I can cancel dl. What is left is E1 minus E3. E1 is the electric field on one side of the surface. E3 is the electric field on the other side of the surface. If I take the scalar product with this vector parallel to the surface, this is 0. This should be 0. So this tells me that the parallel component of the electric field is continuous. So what we had, we started from the divergence of the electric field and showed that the perpendicular component of the electric field, it is discontinuous, and the discontinuity is sigma over epsilon 0. This is the change in the perpendicular component of the electric field as we go from one side of the surface to the other side of the surface. And from the curl of the electric field, which we know is 0, we can say that the change in the component of the electric field parallel to the surface is 0. Now, eventually we will be dealing with problem, for example, the refraction of light. The light, we will see that it's an electromagnetic wave. And as an electromagnetic wave, as it goes from one medium to the other medium, we will see that just using that the perpendicular component of the electric field is discontinuous and the parallel component is continuous, we will be able to drive the Snell's law. But of course, in medium, things will be a bit modified and we will be able to calculate this refraction coefficient, etc.
Peki hocam, küresel bir yüzey alsak, o zaman elektrik field'ın paralel komponenti ne olacak?
Well, you see here, this is an arbitrary surface. When we talk about the parallel or perpendicular components, you are looking at a single point on the surface. And the electric field at that point, from that point you can cross the surface from one side to the other side. The perpendicular component of the electric field from one side of that point to the other side of that point is discontinuous if there is a surface charge at that point, and this is the perpendicular component. The parallel component is continuous across that point on the surface. So it's independent of what kind of a shape you have. At every point, you can talk about the component of the electric field at that point parallel to the surface and perpendicular to the surface. Just like the r hat vector. At every point, you have a different r hat vector. If you have a curved surface, the parallel direction is different at every point, and the perpendicular direction is different at every point. So here, the discontinuity, the changes as you go from one side to the other side of the surface is across that point, and the parallel and perpendicular are defined at that point. We are not specifying the global shape of the surface, any surface. Because we are just looking at a single point. We are crossing that surface across a point, through a point.
Burada integralde D'leri sıfıra yaklaştırdık ya. Böylelikle ikinci ve dördüncü yüzdeyi yapmış olduk, sıfırlamış olduk. Yani D'yi niye sıfıra götürmek zorunda mıyız? Götürmesek de aynı sonucu elde edebiliriz.
Well, you see, the problem is I want to relate the electric fields on both sides. If D is non-zero, you see, let's have this surface. Now, the electric field at this point, in general, will be different than the electric field at that point. So the parallel component of the electric field here will be different than the parallel component of the electric field at that point. But we have seen that the parallel component of the electric field at this point and the parallel component of the electric field at that point are the same. But the parallel component of the electric field at this point and the parallel component of the electric field at some other point, they are different. So the parallel components of the electric fields between this point and this point, these big dots, they will be different. I cannot say anything about the parallel components of the electric field between those two. The only thing I can say is if those points that I am comparing are just on the two sides of a surface. Those two I can relate. That is why I need to take D equal to 0 over here. So that line 1, segment 1, and segment 3, they lie on the surface on opposite faces of the surface. And hence I can relate the electric fields on the surface. It's just on the opposite sides of the surface.
Can we explain with another way why the curl of E equals 0, right?
Well,
With this law.
Well, the curl of E is always 0. Well, we had these two explanations. Once we evaluated the electric field over a closed loop, we showed that the integral of the electric field over any closed loop was 0. But that basically means that the curl of the electric field is 0. That is one way. The other way was okay, this is method 1. The other method we used was we used this explicit form of the electric field. Because no matter what, the electric field is created by charges situated somewhere in the universe. And we might not know the charge distribution, but we know that there exists a charge distribution of these charges. And the electric field and those charge distribution is related through this integral. Again, as I said, we might not know what rho of r is, but in this derivation proving that the curl of the electric field is 0, we don't need to know what rho is. We know that there is one rho. In terms of that rho, we can always write the electric field in this form, And if we can write the electric field in this form, the curl of the electric field is 0. For example, when we start studying electrodynamics, we will see that not all electric fields can be written in this form. And since not all electric fields can be written in this form, the curl of not every electric field is 0. But in electrostatics, the curl of every electric field is 0. That is something I should underline. Curl of the electric field is 0 in electrostatics. The charges are not moving. All the charges are at rest. Or let's say we are in a reference frame in which all the charges are at rest. Otherwise, this equality will not hold.
Can we say that electric field is conservative since it's not dependent on time?
Yes, it is a conservative field. And hence, we will be able to define an electrostatic potential next week, on Tuesday. They are recording you. Well, there was one point which we had, well, there was one question in one of your pre-reports asking, okay, so if there is an electric field line passing through every point, then the density of the electric field lines is infinite. So how can we talk about the density changing, etc.? Now, the thing is, when we are talking about electric field lines, what we know is we know that at every, if the electric field is non-zero, there is an electric field at every point. So we have to draw a vector at every point. Electric field line is a line that is tangent to these electric field vectors. So, in a sense, at every point, since there is an electric field vector, there is a line. There is an electric field line passing through that point at every point. So you cannot just count the electric field lines one by one in a strict sense. But what you do is, for practical reasons, you first set up your convention. Per coulomb, how many electric field lines will you draw? Well, you should be drawing infinitely many because there are infinitely many electric field lines, but you first fix your convention. You say that, okay, per coulomb I will draw 10 electric field lines. For example, in this figure, I didn't draw an electric field line in this passing through that point. It's not because the electric field at that point is 0. It's just I cannot draw infinitely many lines. So I just fix my convention. I will draw a finite number of electric field lines. But of course, that means if you draw a finite number of electric field lines, that means there won't be an electric field line passing through every point. So there will be such gaps over here. But although there are gaps, you can still talk about the average density passing through a point. For example, if I want to find the electric field at that point, I mean, how do you define the density of electric field lines? You basically take an area, count the number of electric field lines passing through that area, divide by the area, that is the density. Well, if you assume such an area, well, there are no electric field lines passing through it. So you cannot choose such an area. You have to choose, let's say, such an area and count the density average. It is just like, for example, we can talk about the mass density of this one. We say that this is continuous. In reality, it is not. There are point masses in it. And between those point masses, the mass is 0. So if you could measure, if you could look at distances much, much smaller than, let's say, atomic separation, you will see many points that have 0 mass. But to define the density, and when we say that this is homogeneous, we don't look at take such a small volume. We take a volume that is large enough to contain many atoms, and then define the average in that sense. Here, the average is also defined in a similar sense. I mean, you first set up your convention of how many electric field lines you will draw passing through for a given charge. That is your convention. So you draw as many as you can. And when you are talking about the density, that is the number of electric field lines passing through a given area, you have to choose an area large enough that it will contain many electric field lines passing through it. And then talking about the density of the electric field lines will make sense.
Hocam şimdi yani iki tane elektron düşünsek, böyle birbirine mümkün olduğu kadar yakınlar. O zaman elektrik field aralarında bir boşluk oluyor işte o çizgiler arasında.
Okay, through that point in the middle, no electric field line passes. There is a single point through which the electric field line does not pass. Any last questions? So see you next week. Don't forget your homework. It's not to class.